Okay, so as in the last video, we completed the derivation of the displacement for finding the displacement, right? What was the formula for it, or what we found the formula for it? The formula for finding the displacement of the projection of a particle which moves along a uniform circular path is x is equal to r cos theta, and theta, where we know that, is actually omega t. Omega is velocity, angular velocity, and time, right? So x is equal to either r cos theta or x is equal to r cos omega t. Then we talked about the maximum displacement and the minimum displacement. The maximum displacement would always be on the extreme position, no matter it is uniform circular motion, or it is a simple pendulum, or it is motion under elastic restoring force. The maximum displacement would always be at the extreme position, since displacement is always taken away from the mean position, right? And the minimum position is always at the mean. The minimum displacement is always at the mean position. The maximum displacement we found was x is equal to r, where displacement equals to the radius of the circle. That is the maximum displacement, and the minimum displacement was of course 0, right? In today's video, we are going to derive the formula for finding the velocity, of the projection of a particle which moves along the circular path, right? So what we are going to do today is, we are going to derivation for the formula of velocity. For the formula of velocity, right? So today we are going to do what? We are going to derive the formula for the velocity, for finding the velocity of the projection of a particle. Okay, so let's make the circle again. This is our radius, and this is our center point. Here we have our particle which is moving, right? Which is moving. Now see, we have already talked about it. This is our radius. This is our radius, right? And here we're gonna have the projection of the particle. The projection of the particle, right? Here we are gonna have its velocity, which we are naming it as vq, right? And here we will have the particles tangential velocity, right? We have already discussed about tangential velocity. So this is what? This is tangential velocity. Let me write this here. This is tangential velocity. Okay, this is tangential velocity. Now see, we need to make, or we need to break this vector in its components, right? So one would be this component and another would be this component. I must make this with another color, right? One would be this component and other one would be this component. Now see, this vector is making angle with this, so which means this is its x component, vpx, right? And this is its y component, vpy. Now see, which component of a tangential velocity, let me write this, this is a mean position, right? Now see, which component of the tangential velocity is responsible for the speed of the particle, for the responsible for the projection speed. Now see, vpy is responsible for the speed or for the velocity of the projection of a particle. See, both have the same direction, vpy, right? and Vp, not Vp, however Vq, right? Both have the same direction, which means Vp x component is not responsible for Vq's velocity. However, Vp y component is responsible for the velocity, right? So let me write this here. God. Okay, no problem. Let me write this here. Vpy component of velocity is responsible for the shadow's velocity or for the projection's velocity, right? Projection's velocity, which means Vpy or Vq would be equal to Vpy, since Vpy is responsible for Vq velocity, right? Now if I remove this y, I'll have sine theta, Vp sine theta, right? Because we have already talked about this in the vectors chapter, right? So Vp sine theta. Now we know that in a uniform circular motion the tangential velocity is equal to r omega. The tangential velocity is equal to r omega. So let's substitute this. Vq is equal to Vp, not Vp, but here now what will we have? Instead of Vp, we're gonna have r omega sine theta, r omega sine theta. And we know that sine square theta plus cos square theta is equal to 1, right? We want sine theta's value. So sine square theta is equal to 1 minus cos square theta. See, we don't want sine square theta, we just need sine theta. So radical on both sides, right? So this square would be cancelled. So sine theta is equal to radical 1 minus cos square theta. Let's substitute sine theta value in the equation, right? In the equation. So what it became now, Vq is equal to r omega. Instead of sine theta, now I can write here 1 minus cos square theta, right? Radical 1 minus cos square theta. And cos is equal to what? This we have already learned, that cos is equal to base upon hypotenuse. Cos is equal to base upon hypotenuse, right? Now Vq is equal to r omega radical 1 minus, now see, instead of base we have what? Instead of base we have actually x, right? Since this is displacement, so now I can write x square upon, instead of hypotenuse we have r, so let's put r square, right? Let's take LCM of it. Vq is equal to r omega radical 1 minus, not 1 however, now here r square minus x square upon r square, right? When we took LCM we got r square minus x square upon r square. right? Now VQ is equal to this r square can be can come out from the radical, right, since it is in radical. So r omega radical r square minus x square upon r, since this square cancelled with the radical, so this r cancelled with this r now. So what we got, our final formula VQ is equal to, now see, instead of radius square you can actually write x naught square, because x naught is equal to amplitude, it is equal to the displacement, right, maximum displacement. So x naught square minus x square. This is the final formula for finding the velocity of the shadow of a particle which is moving along the uniform circular path, right? So what we have got, our final formula, omega radical x naught square minus x square, final formula. Omega radical x naught square minus x square. In the next video we're gonna see the maximum displacement and the minimum displacement.